Okay, good afternoon, everyone. Do you have any questions before I get started?
Yeah, I had a quick question about the homework.
Yeah, what is it?
For number 2, just in general, if we're in the set of natural numbers, are we including 0 or no?
Yes.
Okay.
The book, the book we're using includes 0. So I am including zeros as well. Okay?
Okay, thank you.
Sure. Any other questions? Okay. So let me ask you a simple question just to get started. True or false? Okay. This is my question. Suppose A, B are integers. Let's see. My question that if A divide B and B divide A, then A equal to B. Okay? True, you justify, and false, you justify. Remember how to show that something is false and how we show that something is true. So this is an if then statement. That's my hypothesis, my conclusion. Okay, any input? All right, you go quiet. Any ideas? Any feelings for it? All right, what are you doing? Can you use that A divide B implies A less than B? All right, less or equal, right? So the question is, suppose A is less than B, then it means A strictly less than B. Is this a true statement? I'm saying you have to be less or equal because let's just understand if A less than B divide B, it means that B equal to K times A. So let us analyze. Is the statement correct? So A divide B, it means B equal to A, K times A. So is A less than B? Okay, who would like to talk about it? And why is A less than B? If I want to prove it, how can I prove it? How can I prove it? Okay, suppose A bigger than B. Okay. All right. So what do you think? Remember my numbers, we'll then be dividing A would be a contradiction. There is one thing that I would like to point out, that my numbers could be negative. And let's see if this helps you at all. So my question is the following. Is this a true statement? 3 divide minus 6. Is this a true statement according to our definition of divide? Is this a true statement? That 3, yes, because, so that's true, because minus 6 could be written as minus 2 times 3. So whatever your classmate is putting, he is right, as long as everything I'm working with is a bunch of positive numbers. So the question is, so according to us, this is true, okay? A is 3, you divide minus 6, but is A less than B? No, because minus 6 is not, 3 is not less than minus 6. All right, so what's really true is the absolute value will be true. Okay, so the only thing here is that my numbers don't have to be positive. If my numbers are positive, then absolutely, you guys are absolutely correct. So if A divide B, then the absolute value of A is less than the absolute value of B. That's a correct statement. If my numbers are not necessarily positive, then this is not really going to hold. And now I go back to my question. Do you think is it true or false? So this is a nice problem. I will actually assign it to you as a homework. Okay, show that. But I'm going to go back to here. It is false. So how do you show it's false? How do we show that something is false? Okay. To show that something is false, you have to give me a counterexample. Means you have to give me 2 numbers, such that the hypothesis is true and the conclusion is false. Okay, so let us see, I'll pick up. Okay, so let's take A to be minus 3 and B equal to 3. Now A divide B, because 3 could be written as minus 1 times minus 3. B divide A, because A, which is minus 3, could be written as minus 1 times B. But B, A is different from B. Okay, so if I do not require both of them to be positive, then the statement is false. However, if I require A and B to be positive, the statement will be true. And I will assign this as a small homework for you. Okay. All right. Another small problems to do before we, for the next few days, the only thing we'll be doing is, learning how to prove. Question number 2 is the following. Suppose I ask you to show that, prove that the product, very simple statement, that the product of 2 consecutive integers, sorry, I forgot how to spell that. It's VES, I guess. The product of 2 consecutive integers is even. Okay, so prove that the product of 2 consecutive integers is even. So before we do that, let us write it in, in this form, if, then, and for every. So for every, if, then. So actually, we don't. Okay. So let's write it in a simple format that we can all interact with it. Actually, we don't need if then in this statement, my apology. So what do I want to prove? The product of 2 consecutive integers is even. So how can you write it in a sentence that we can understand? That's what I mean by that. Given any n in n, or actually in z, given any n in z, the product of two consecutive integers means n times n plus 1 is even. Okay, a very simple statement. If you take any integers, you multiply two consecutive integers by each other, you're going to get an even number. How can I prove something like that? Intuitively, it makes sense, of course. And how do we prove it? Okay, I'll give you 2 minutes to interact with it, and then we take it from there. So it's not really if-then, my apology here, but it's a statement. The product of two consecutive integers is even. So that's the best way to write it. Yn plus 1. What does consecutive mean? Consecutive mean one after the other. Okay, that's what we mean. Like 2, 3 are consecutive integers. 3, 4 are consecutive integers. That's what we mean by consecutive integer, one after another. So now my statement is given for all n in n times n plus 1 is even. How can I do a simple proof like that? Even though it's not if-then, but really it's the same idea. So because I don't have if-thens, I really sometimes I don't know how to start, but we should be able to.
Would we have two cases if we choose n to be an even or odd number?
Right, that's a good idea. I don't have if-then, so I really don't know exactly what my hypothesis is. I don't really have much of a hypothesis, but no matter what n is, I have to show that this product is even. So one good way here is that, I have to take cases. Case 1, and my cases should cover my whole domain, I mean everything. Case 1, assume n even. And case 2, okay, if it's not even, n has to be out. Okay, so now cases kind of impose themselves on us. So they tell me that, okay, so if n even, I want to show you that then this would be even. If n is odd, I have to convince you that this is odd. All right, so case 1 n even. Now let us do that. So that's I'm assuming n even, and I want to convince you at the end that n plus 1 times n plus 1 is even. It means 2 times an integer. That's really what I have to convince you. All right. Okay, what does mean an even? An even means, by definition of even, I can find an integer k in Z such that n equal 2k. Okay, so that's where even is. It means it's 2 times k. But now it's not that what I care about. I care about n times n plus 1. So now we're going to compute n times n plus 1. So n times n plus 1 equal 2. So that's really what my goal is. So I never lose track of that. That's where I'm heading. It's 2k times 2k plus 1. And now I want to write this as 2 times an integer. So I write the 2 here, and then k times 2k plus 1. Now this is my integer. I see it, and I know it's an integer because k is an integer. I'm going to call this is my j. So I'm going to put j to be k times 2k plus 1. And this is, of course, an element is an integer because an integer times an integer, we're assuming that's an integer. So it's equal to 2 times j, where j is in Z. So by definition, I'm erasing that. So n times n plus 1 is even by definition of even. Okay, so sometimes the problem, even if we don't have a very clear-cut hypothesis, we can handle it by taking cases, especially in a scenario like that. Now, case 2, an odd. Okay, an odd. An odd means, it means we can find an integer, so they're totally separate case. So even I can use the same k because I'm totally doing another case. Means I can find some integer k such that n is the 2k plus 1. Okay, but my goal is really not n. My goal is n times n plus 1. That's really my goal. So that's really what I'm heading toward, and that's what I go after. So now I try to evaluate this. And what do I get? N is 2k plus 1. N is, that's 2k plus 1 plus 1. Okay, and now how am I supposed to get to 2 times an integer? Okay, all right. Simple questions. I want an answer from you because I want you to help me write everything. Okay, how do you want me to get to 2 times an integer? What do you want me to do? Let's start picking. Rachel, what do you want me to do? Rachel, are you with me?
Yeah, I'm with you.
Okay, what do you want me to do? I have to get to 2 times an integer. What do you think I want to do? So what do you want me to do from here to here?
My first instinct says to distribute the parentheses and combine them, and then we can eventually take
The 2 away.
out to read
Yeah,
the integer.
we can do that, but that's a little bit the long way. Why I'm saying that? What's 2k plus 1 plus 1? Now, nobody want to keep this.
2 out of that.
What?
You could take 2 out of 2k
Now
plus
I can take the 2 out. Okay, so this will be easier than really distributing. So this is 2k plus 1 times 2 times the k plus 1. Okay, now of course I'm going to erase this. I know that. So now I rewrite this as 2 times 2k plus 1 times k plus 1. Okay, now I don't have to distribute because I know that this is going to be my integers. So this is going to be 2 times, this is my integer, 2 times my integer. So you can introduce the j and rewrite it like this. All right, so by definition of even, n times n plus 1 is even. Okay, so now this is a result you can use all the time, that if you multiply 2 consecutive integers by each other, always the product is going to be an even number. It makes sense, like 2 times 3, 2 is even. So the product is even. 3 times 4, so whenever you multiply 2 numbers by each other, one of them will have to be even, causing the product itself to be even. But this is really, how we will prove it mathematically that this is the case. Okay. Right. Now I'm gonna, as we build up, build up slowly proof, we have to introduce definitions so I can give you more problems. So we're gonna define a prime number. So definition. What's a prime number? Of prime number. Okay. Right. So let p be an integer which is bigger than 1. So let p be a positive integer with p with p strictly bigger than 1. Okay, so let p be a positive integers with p strictly bigger than 1. And that's very important part of definition. Then p is called prime. P is called prime. And definitely, I'm going to rewrite the definition. You know what a prime is. P is called prime if it's only positive factor, or this only divisor, if it's only positive divisors are what and what. Okay, a number is prime if the only number that divide p are, who want to finish my sentence? Who want to finish my sentence? Are 1 and p. So that's a prime number. Like 3 is a prime. The only number that divides 3 are 1 and 3 itself. So that is a prime. 1 is not a prime. And this has to do with something called the factorization of prime number, the factorization of prime numbers. So P1 is not considered a prime, but a number bigger than 1 is called a prime if its only positive divisors are 1 and 1. So it means P prime means P is bigger than 1, and whenever P equal A times B, with A and B integers, of course, if P is equal, A and B are integers, and that's crucial, then either A is 1 and B is P, or A is P and B is 1. Okay, so a number P is called prime. I'm trying to see to fit the whole thing here. This is better. Yeah. So P is prime means P is a number bigger than 1, and if P is A times B, where A and B are integer, then either A is 1 and B is P, or A is P and B is 1. Okay, so this is what a prime number. So what's a composite? So I'm going to write definition of a composite. P is called a composite if it's not a prime. So a number P is called composite if P is not a prime. Okay, so what does this mean? It means that if we can find two integers, A, B in N, such that P is their product. If I can find two integers, A and B, such that P is the product, and both of them are bigger than 1. Okay, so a number is composite if I can write it as the product of two integers, but both of them are bigger than 1. It means neither one, this could be 1, nor this could be 1. So if both of them are bigger than 1, it means P cannot be broken. The situation cannot occur. Or I say a number is composite intuitively if you can write it as the product of two numbers, neither one of them is P or 1. A is not P or 1, B is not P or 1. It means both of them has to be bigger than 1. One more definition, and then we take a small problem, which you guys will have to use all those definitions. Perfect square, since perfect square give us a property of a lot of problems, use the notion of perfect square. So definition of perfect square. Perfect square are basically the following numbers: 1, 4, 9, 16. These are the perfect square. So let us really write them down. So a number n, let m be in n. In n, there we say that n is a perfect square if n is k squared for some k in n. Okay, so let n be an integer, I mean a natural number. We say that it's a perfect square if it's equal to k squared for some k. So example, 1 is a perfect square because 1 could be written 1 square. 4 is a perfect square because it's 2 square. It means what's the k here is 2 in my problem. Then 9 is a perfect square because it could be written as 3 square, and so on and so forth. So these are the perfect squares. So 1, 4, 9, 16, 25, you guys know the rest. So those are the perfect square. So now we define two definitions. What's a prime number? What's a composite number? And what's a perfect square? I'm going to give you a very small problem where you use all those definitions so you'll be comfortable using them later on. Okay. So this is my problem, very simple one, a small proof. So example. Okay. So suppose I tell you let n be an integer. Actually, n is n with n bigger than 4. So basically, this is my domain. Okay, so let n be an integer with n bigger. Prove the following. Show that if n is a perfect square, so now I am so show that if n is a perfect square, then n minus 1 is not prime. It means n minus 1 is composite or not prime. Okay, so this is a if and then statement. So my domain is a number larger than 4. And I want to tell you that if I take a number, if it's a perfect square, then n minus 1 cannot be prime. So let us, if I take 4, so it's bigger than 4. So let me take, let me take a perfect square, 9. 9 minus 1 is 8. Definitely it's a composite number. 25 minus 1, okay, that's also a composite number. However, if I take n, and 4 is a perfect square, 4 minus 1 is prime. That's why I need the condition n bigger than 4. All right. So first, what's my hypothesis? That's my conclusion. And we need to prove this. So what should we start with? And what is our goal? Okay. So what do we start with? We start with n in n, which is bigger than 1, that satisfy this property. And we have to show that if it satisfies this property, so it means it's a perfect square, then n minus 1 is composite. All right. Okay, I definitely want you to work on this, but let's see what's going to be our first sentence in the proof. Let n be in n with n bigger than 4. Now I'm picking something in my domain. But in a proof, in an if-then proof, I have to assume that my n satisfy the hypothesis. So let n be such that the hypothesis is true. N is a perfect square. So I'm not talking about any number. I'm talking about very specific number. Those who are the square of something. I'm talking about the 9s and the 25 and the 36s and the 49. That's really what I'm talking about. That's my n. N is a perfect square. And then my goal is here. That's really what I'm going to aim for. I need to aim to show that n minus 1 can be broken. This is composite. Means I can write it as the product of two numbers. Both of them are bigger than 1. Okay? So I give you a few minutes, like 3 minutes to interact with it. And we're gonna discuss it. We use the definition. That's why I have this problem, to make sure we know the definition. What's a perfect square? What form they have? That's crucial. What's a perfect square? What does it mean to be composite? If you want to show me it's composite, what do you have to show me? Means we can write as the product of two numbers where both of them are bigger than 1. Means none of them could be 1 and the other p. Both has to be bigger than 1. That's composite. All right. Okay, 2 minutes. I know that I see stuff on chat, but I want everybody to interact a little bit with the problem. So that's a very direct proof. That's my hypothesis, my conclusion. And I'm going to pick one of you eventually to just start helping me out. Patrick, can you tell me what you're doing? And are you right?
Sorry, I showed up a little late. Kind of trying to catch up.
Okay, I won't put you on the spot. Next time, show up on time, because I don't keep up exactly what time you guys showed up. I try to. Nick, are you with me? Nick, are you with me? All right, anybody else? Logan?
Yeah, I'm here.
All right, get me. Let's do it together.
What I'm trying to do is I'm trying to show that I say for like every k there exists there exists a k such that n is equal to k squared. But I'm trying to figure out what to do from there.
So
stuck
far
with-
you're using the definition, right?
Yeah.
Okay, what do you want to prove? What is my goal at the end? If you don't put your goal, you're lost.
I'm proving that n minus 1 is not equal to k squared.
No,
Is that? Oh, it's composite, so it's a times b.
right. When
There
I
you go.
prove that it's composite, means when I prove that we can write it as a product of two numbers, two integers, of course, and both of them bigger than 1. It means none of them could be n minus 1 or 1. With me?
Yeah.
Okay, so that's my goal. I mean, that's really what you should be looking at. So, but we have to use what's
All right.
special.
So then do I replace k squared or n by k squared and n minus 1?
Okay. All right. And now remember what we have to do. We want to see how you have to convince me that you can actually split it, write it as a product of two things, which are integers.
Would be k plus 1, k minus 1.
Yeah, that's, k minus 1, k plus 1. Okay. All right. So now we wrote it as a product of two integers. Are we done? To show it's composite, it means you have to show that you can write it as the product of two integers.
Yeah, but if we show like, say if we say k or n is equal to 5 or k is 5, anything, it won't fit the constraint of k being greater than 4. I don't know how to.
I'm listening. You're on the right track. What
So,
are you
like, with-
trying to
So,
say?
like, so if you say, like, for instance, k is equal to 5,
Yes.
then it won't fit the n is greater than 4 constraint.
Okay, so we're going to think backward in a way.
All right.
So what are you trying to say? You have to convince me, convince us that you wrote it as a product, but now you have to make sure that both of them has to be bigger than 1. Otherwise, k minus, this doesn't mean that it's a composite. Those has to be bigger than 1. So we have to make sure that this one cannot be 1, and this one cannot be 1 also. Otherwise, we'll not have a composite. Now, why is k minus 1 bigger than 1? How can I get to that? Go ahead.
Well, we know that n is bigger than 4, so
N is bigger than 4. Very good. What does this mean? Keep your train of thought. What is n?
should we k squared?
Means k squared bigger than 4. Everything is positive. I'm working really with the natural numbers. So if k squared bigger than 4, k should be what?
Bigger than the square root of 4, or
Yeah, which is
2?
what?
2?
Which is 2. So it means the large k has to be strictly bigger than 2. It means k is basically, that's an integer, it's bigger or equal to 3. So can I say that k minus 1 has to be strictly bigger than 1?
Yeah.
And k plus 1 is strictly bigger than 1.
Yeah.
So now I wrote my number as a product of 2 integers, both bigger than 1. It means definitely it's a composite. None of them is 1, and none of them is n minus 1. They are both bigger than 1. All right? That's how we're going to do it verbatim. So let's rewrite it down. N is a perfect square. Hence, I can find a k in n such that n equal k squared. That's what I got. And the domain is important, as you realize. Without my domain here, I'm really in trouble. So that's what I want. I want n minus 1. So I go after it. So okay, now let's look at n minus 1. I substitute. Okay, so we're going to substitute k squared for n, because n minus 1 is equal to that. And now, because we know some algebra, that's going to be equal to that. Okay, now I have to make sure that those, because if I want to show it's composite, I have to make sure that neither this nor that is 1 by showing that both of them has to be bigger than 1. So now I say, okay, but n is bigger than 4. So here now I write that to show that's what I want after that. K minus 1 bigger than 1 and k plus 1 bigger than 1. Both are bigger than 1. It means neither one of them could be 1. It means it's a prime. All right, so now I said, okay, but then what is k? We know that n is bigger than 4. It means my k squared is bigger than 4. So k has to be bigger than 2 because k is positive. I'm working in n. So k is positive. So I don't have to worry about k less than minus 2. Okay? So this means that k minus 1, so hence, if k bigger than 2, k minus 1 has to be bigger than 2 minus 1. It means k is strictly, it means k minus 1 is strictly bigger than 1. Because k is basically the smallest value k take is 3. So k minus 1, the smallest value it's going to take is 2. So it's bigger than 1. Also, of course, k plus 1 is bigger than 2 plus 1, which is equal to 3. Okay, so hence we wrote, hence n minus 1 is written as the product of 2 numbers with both of them bigger than 1. and k plus 1 bigger than 1. So they are, it means k minus 1 is a divisor of n minus 1. It's definitely not 1. It cannot be n minus 1 either, because k plus 1 bigger than 1. Because if k minus 1 is n minus 1, it means k plus 1 is 1. And we know that this is not the case. Okay, so n minus 1 is composite. All right, so this is like a small problem where we have to put what we've learned and combine them into a little bit of a proof. So please ask questions as I go on. Okay, now we're gonna move to chapter 9. So it's all those chapters 9 and 10 are really the same thing, but I'm gonna, before I move to chapter 9, I'm gonna actually put the following problem on the board. I mean, not on the board, on a sheet of paper. Prove the following. If you guys have a scratch piece, just use a scratch piece. Prove the following. Let them be in Z. Okay, show that. If n squared is even. So last time we proved, let me remind you what we proved last time. Last time, if my memory is proved, we showed that if you take a number n even, then you square this number, then you also get an even number, okay? Now I want to ask you the following. I want you to prove that. If I take a number, I throw a number at you, and I told you I have a number in my mind. When I square it, it's even. Can you conclude then n is even? Okay, so this is my problem now. Prove the following. Let n be in Z. If n squared is even, then n is even. So this is my hypothesis now. And this is my conclusion. Okay, and you want to prove this. So remember, now the number n that I have in my mind has the property that when you take it squared, it's even. I want you to convince me somehow that the number n itself is even. Okay, so we pick an n in n. I don't know, you guys work on it. Again, 3 minutes, work on it. And then I will pick one of you. All of you stay with me because I will pick one of you and you guys tell me what you came up with. Whatever you came up, I don't really care whether it's true or false. And we discuss it. So we're gonna use direct proof. So we assume the hypothesis is true and try to get to the conclusion. Okay, let me pick somebody. Patrick, are you with me now?
Yeah, I'm more or
Okay.
less with you.
Yeah, all right. So let's see, what did you do?
So, I mean, the statement is just false, right? Like, or am I missing a conditional statement on top?
I'm telling you prove it. So I did not ask you true or false. You're not
Okay.
missing anything. So how do we start to prove? Let us start it. So
Okay,
we pick- yes.
let n and z, then for all n and z, n squared is going to be, oh, I see. Okay. I was mixing up negative and positive and odd and even. Okay. This is so much easier than I thought it was. I was like, this is just completely false. Okay. If n squared is even, then n is even. Okay. So for n and z, n is even, and k and z, k is even, then nk will be even, I guess.
What's your hypothesis here?
My hypothesis is n squared is even, right?
Yes. So what is it what you have to prove, to show me?
I have to show that n is even if n squared is even.
Okay, so what do we start with?
Assume n is even. How about that?
That's the way. That's what I want.
Okay.
Assume the hypothesis hold.
N squared is even either way.
That's my hypothesis. Okay, so we're doing what we're gonna call, what I call direct proof. Okay.
Okay. Yeah. Okay.
That's
so
my-
assume n squared is even.
Yes. So guys, write on a scratch piece of paper. We're just trying to analyze this problem.
N squared is equal to n times n.
No, yeah, sorry, yes. Keep going.
So n is equal to n, which is n squared divide n. So n squared divide n equal n. An even number divided by any number will yield an even result. Is that a valid proof or no?
Okay, so let me follow you verbatim. All of us follow, and we're gonna, see. So you're isolating your n, right?
Yeah.
Okay, and you're telling me n squared is even, correct?
Yeah.
So how do we characterize even? What's their properties?
Equal to 2k.
Right, it is crucial.
For some k and z.
Very good.
Okay.
2k where k is in z. Okay? So n, according to you, I'm following you verbatim, is equal to 2k over n. Am I right so far? Am I following you?
Yeah.
Very good. How are you gonna, why is n even?
Okay, so for 2k divide for n divide 2k to be in z, I guess. If that's in z, then it has to be. How do I say this? It has to be even.
You're right. If k over n is in z, then n is even. But so now, what's the big question?
Is k in z?
K, yeah,
No,
k is in
we've
z.
already said that k is in z.
Right. So what's my big issue now? So far, everything we wrote is correct. And anybody wants to pitch in? It's k over n. So now that's the big question.
Is k over n and z? Oh, okay.
That's the big question. And somebody tell me yes, and I don't, if you say yes, you have to justify.
Oh, because n's in z, right?
No, yeah, n is in z, but why k over n is in z? I have no idea.
Well, I guess, yeah, because 2k over n could,
It's k over n in z. I don't know k and I don't know n basically, right?
yeah.
Because I told you, I know the only thing I know that n square is 2 times k, but I really don't know what k is. I don't know what n is. So the problem is k over n in z. And the student who said yes, justify. No, I have an issue with that. I will get back to it. So is k over n over z basically, honestly, I have no idea. No idea. Okay, now, that's the problem. I don't know whether it's in Z or not. So if you want to tell me yes, the student who said yes, why you say yes? In mute and explain.
Oh, wait. So we've assumed that n squared is even. Okay, so k must be larger than n, I want to say.
I don't know why though. Why I mean, if you take 4, suppose I take n, let me suppose I take.
So because we've assumed n squared is even,
Yeah.
we've assumed by definition that k is greater than or equal to 2 if k is in z.
Okay.
So given that k is greater than or equal to 2, for 2k over n to be equal to n, k has to be in z then. It's
K is in z.
Sorry, for 2k over n to be equal to a to be equal to a number in z that and k bigger than n.
Why k is bigger than n? I'm
n.
having issue with k bigger than n. Is k bigger than n? I don't know why. We cannot claim anything that we cannot show. Why is k bigger than n?
Because
if I take 4, it's 2 times 2, right?
Yeah.
What's your k here?
Okay, bigger than or equal to n, sorry. And only equal to n in the case of 2, but
There we're in trouble. I'm in trouble. Now, I'm going to take the last remark that I saw on chat. Logan, explain yourself.
I was just trying to figure out some kind of algebraic way to get rid of the denominator, but it didn't work out too well.
Yeah. Is n equal to k? Do we know anything about n?
It's that was the issue. It's n squared, so
Right, exactly.
that's
Nothing.
where it's up.
So we're struggling. Honestly, we're struggling. So we're starting with n squared even. Every word you guys wrote is correct. But I got stuck right here. Right here is k over n an integer. Okay, and every argument you gave me was wishy-washy, not really a strong argument.
Wait.
Wishy-washy doesn't go far in math.
let's just assume that n squared is odd, right? Doesn't that make this easy?
And n squared is odd?
Yeah.
I can't assume n squared is odd because the hypothesis tells me n squared is even.
Oh, okay, fair enough.
Right? That's my hypothesis. I can't really play with it. That's what's given to me. All right? So, of course, we have to prove this. And the way we did it.
Wait. No,
listening.
that doesn't work either.
Okay, right. So that's we're struggling, and that's crucial to struggle. I mean, that's how things work in math. We have to struggle. All right, so the idea is we need a way to solve this problem by not going directly. And we're going to introduce another way of proving statement, which is not, some of you already wrote it on chat, but that's not the point. Another way to prove statement, which is not what we call a direct proof. We're going to introduce something called proof by contraposition. So, which is, I think, chapter 9 in your book. So, proof by contraposition. And let's see what is it about and how to handle it. Because as you realize, we're struggling. We're struggling for sure in this statement. So, chapter 9, proof by contrapositive. Okay. So direct proof is the best, but sometimes we're stuck, and that's really what's happening in this. And you have to feel we're stuck. I mean, I wanted you to do it because I want you to struggle with this problem. So what's the idea of proof by contrapositive? First, let us see what it means, what it is. I go back to this problem. Okay. Do you guys remember what's the contrapositive of if-then statement? What's the contrapositive? Guys, remember? Anybody?
It's like if the negation.
No. Let's see what the contrapositive is. So let us recall. Remember, your exam is on Monday. Let us recall. Suppose I have the following statement. Okay. So the contrapositive of, okay, for all x in D, if P of x, then Q of x is. So the contrapositive, no. The contrapositive of, for all x in P, if P is for all x in D, that doesn't change. If non-Q, then non-P. Crucial. Okay, so the contrapositive of the statement, if P then Q, is if non-Q, then non-P. So let's rewrite the contrapositive of the statement. So let us consider the statement. Okay, all right. My statement is, for all n in Z, if n squared is even, then n is even. What's the contrapositive? The domain does not change. If, then, the contrapositive if non-Q means if n is not even, which is n is odd because that's what not even is, then n squared is not even. Okay, so that's the contrapositive. If n is not even, then n squared is not even. You guys, is your memory being back? Okay, you guys remember now? So that's the contrapositive. Now, what's the benefit of the contrapositive? What's the important thing about the contrapositive? Suppose, before we write all the logic stuff, suppose I convince you, and very easy we will, that this statement is true. So you don't have to write. Now we're going to think. Suppose I told you that this statement is true. Does this imply this statement is true? Suppose I convince you the following. If n, right, suppose I convince you that if n is not even, then n squared is not even. Can I conclude that this is true? Like, think about it. Okay, and then we talk about logical equivalence. Now think about it. Suppose this is true. It means whenever the number is odd, square it, you get odd. Does this imply this is true? Yeah, because if I start with a number that said n squared is even, it means I want to show you that n is even. I tell you, okay, if n squared is even, I want to convince you that n is even, because if n is not, n squared will not. So if n squared is even, this will have to be even. Otherwise, n squared will not be even. So if this statement is true, this will have to be true. In other words, a statement and its contrapositive are logically equivalent, because when we draw the truth table, this is P and this is Q. This is P, then Q, and this is non-Q, then non-P. If P then Q is true, non-Q then non-P is automatically true. They are actually logically equivalent. If you go back to the truth table, true, false, true, false. If P then Q, I know that it's false in one case. Hypothesis true, conclusion false. And it's true everywhere else. Non-Q then non-P. Sorry, I missed something here. So I'm going to add non-Q, then non-P. I will add one more column. So non-Q will be a false, a true, false, true. Non-P would be false, false, true, true. So let us take non-Q, then non-P. It's going to be false. It's going to be, sorry, true, because that's an implication. True, false is going to be false. False, I don't care. That's a true, true, true. That's true. It means if P then Q and non-Q then non-P, those are logically equivalent. What does this mean to you? It means if a statement is true, its contrapositive is true. If a statement is false, its contrapositive is false. So, and that's going to be crucial. So a statement and it's a statement of the form. If P of X, then Q is logically equivalent. Is logically equivalent to its contrapositive, to the statement if non-Q, then non-P. What does this mean to you? It means to you that if the statement is true, its contrapositive is true. If the contrapositive is the statement is false, the contrapositive is false. It means those two have the exact truth value. So in the proof by contraposition or proof by contrapositive, the idea would be instead of showing the statement true, which is sometimes hard as we realize now, we prove that its contrapositive is true. If the contrapositive is true, then my original statement is true. So let's write this down and then go back to our problem and realize how simple it will become if we think by contrapositive. So proof by contraposition is the following. By contraposition. What does it say? So the first approach of our proof is direct proof. Proof by contraposition. Okay. Instead of proving for all X in D, if P then Q, we show that the contrapositive is true. We show that for all X in D, if the conclusion is false, if non-Q, then the hypotheses have to be false. That's really how I read this. Okay, it means in a proof by contraposition, we assume proof by contraposition. We assume non-Q, and we prove non-P. Okay, immediately example. Immediately example. Okay, it's a very powerful approach to proof. So when we're proving a statement, our first approach is direct. It means we start with the hypothesis and we try to prove our conclusion. And sometimes when we do that, we hit a roadblock like what we did before. So another approach is, assume the hypothesis is false, the conclusion is false. Means assume non-Q is true and show that if this is false, the hypothesis have to be false. It means that if the hypothesis is true, the conclusion is true. That's really what it means logically equivalent. Now, immediately we go back to the other problems and we proceed. So now use this approach. So now we're going to prove that n be in n. If n squared is even, then n is even. Okay, that's what we have to prove. So first, direct proof failed. Direct proof failed. Because I always want you to start directly. So what do I mean by that? It means if I assume the hypothesis and try to get to the conclusion, I actually wasn't able to do it. That's what I mean by failed. So we do proof by contrapositive. So we're going to do proof by contrapositive. It means, so at the beginning I write a lot and then we don't have to do that. It means we're going to show that. We're going to show that for n in n, what's the contrapositive? I'm going to write it. If n is not even, if n is odd, that's the contrapositive. So this is my P here, and this is my Q. This is non-Q, then non-P. Non-P, it means not even. Not even is odd, because then this is non-P. Okay, so that's the proof by contrapositive. Instead of proving the initial statement, I'm going to prove the contrapositive using direct approach. So now what do we assume? What we're going to assume? We're going to assume non-Q. We're going to assume n is odd, which is easy to work with. And we have to show at the end that n squared is odd. So we really flip the problem around, but in a logical way, absolutely logical way. Now we can finish. This is not hard anymore. So assume n is odd. What does it mean? It means I can find an integer k in n, z, sorry, unless I put n along the board. Okay, so let me put n in this particular case, such that n is equal to 2k plus 1. Okay, I put n because I assumed my original integers to be in n. I didn't have to, but that's what I did in this problem. But my goal is n squared. That's really what my goal. So I'm going after my goal, n squared. So n squared is 2k plus 1 squared. I want to show that this one is odd. Means I want to show that my n squared is 2 times an integer plus 1. Okay, so let's do that. It's going to be equal to what? Okay, what? I'm going to factor this out because I want to have this 4. So this will give me 4k squared plus 4k plus 1. Okay. And now I want this to be 2 times an integer plus 1. How can I write this as 2 times an integer plus 1. Is this easy or hard? Can I write this 2 times an integer plus 1? Okay, the plus 1 is given to me for free. I want the 2. I'm going to factor out the 2 in here, leaving me with 2k squared plus 2k plus 1. So this is my integer. And now this is an integer, no question asked, because k, I'm not dividing, I'm adding 2 integers. So I'm going to put j to be, that was my problem previously, plus 2k. So this is absolutely in z. This time I don't have an issue. So this is going to be written to j plus 1. So n squared is odd by definition of odd. Okay. So that's the new approach to proving a statement. Instead of proving the statement itself, using direct proof, which could be hard, we may face hurdle as we did in the previous one, we say, let me prove the contrapositive. It means assume the conclusion is false, which is mean non-Q is true. And so if the conclusion is false, the hypothesis will have to be false. So if the hypothesis is true, the conclusion will have to be true. That's really what the contrapositive is all about logically. Okay? So that's our second approach to proving a statement, which is not direct, called by contrapositive. So the last few minutes, I'm going to put a problem, very simple. We're not going to prove it. We're just going to ask your opinion about it. And see, and next time we will start working more. So suppose you don't have to write, but I want you to see the problem. Suppose I tell you prove the following. Let mn be a bunch of integers. So I have mn, 2 integers. Suppose I tell you prove that. If m times n is even, then m even or n even. Okay. So this is my hypothesis. And this is my conclusion. So I want you for 2 minutes interact with it. If I want to go directly, what do you think the difficulty I may encounter? I give you a minute, still have 2 minutes. I give you 2 minutes to pinpoint the difficulties that we may encounter. So go direct. Analyze the difficulty. So I gave you 2 numbers. When you multiply them, you get even. But I want you to show me that the only way this can happen if one is even or the other one is even. That's really what I'm asking you. That the difficulty comes from having to address 2 cases with the or statement. That's part of it, but that's part of it, but there is another major part also.
Wouldn't it be the
What? Go ahead, Chris. I think Chris.
because like trying to prove it. So this is direct wise, right?
Yes. I want to start direct because that's how I want you to do. I want you to understand the difficulties you face. Okay. So if I start direct, keep going.
So you're assuming that M times N is even,
which means what to us?
which is M,
That's
Yeah.
what I mean.
yeah, 2 times K.
Now, what am I supposed? How can I prove M or N is even? If I solve for M, I'm gonna have that, correct?
Yeah.
Am I facing the same issue I faced before?
Yes.
Absolutely, because I have no clue whether this is an integer or not. I am really stuck straight at the beginning of the problem. So if I'm gonna go direct, that's the only approach I have for direct. So I'm stuck. So that's why I want you always to start directly and understand what the issue is. In this particular problem, I don't really know what K is. I don't know what M is. So I cannot convince you that this is an integer. That's really a scenario to go contrapositive. Okay, assume this is not true, and then show if this is false, then this is false. I mean, show what does mean to be this false. It means assume if I'm in odd and an odd, that's how this could be false, then MN has to be odd. That's the only way it can happen. All right, and that's what we're gonna start next time. All right, you guys know your exam is on Monday. Your homework is due tomorrow. I will put the solution once I have your homework. So it's due tomorrow evening. I hope you guys are doing well with it. I'll put out the solution most probably on Friday, so you guys can review it. And on the announcement on Brightspace, I put the review. The review are not problems for you to solve. You guys have a lot of homework to work with, and practice problem is what you're responsible for, which is basically everything, but you're not responsible for proof. I'm not putting proof on this. We have to work a lot on those ideas. Monday, we will have a class like usual. You can ask me during this class any questions you want about, not the exam itself, about your misunderstanding. So I can answer any question you have about mistake in the homework, something you didn't understand. And the remaining time, we will work a little bit more proof with contrapositive. Okay? Any question before I let you go? So the exam will open at 2, and you have to give it to me by 11:59 Central Time. Any questions? Okay, bye-bye for now.